Well, one of the big problems we have with the definition of the limit of a sequence, apart from the fact that it can be a little unwieldy to work with, or at least takes a bit of time to get used to it, is that in order to know if the sequence converges or not, you have to know what the limit is beforehand to use the definition. And if you know what the limit is beforehand, you already know that the sequence converges. So not really that helpful, right? Do we have a method that would allow us to tell if a sequence converges or not without first having to know what the limit is? We'll say that a sequence is a Cauchy sequence after Augustin Louis Cauchy, who was a French mathematician. If for every epsilon greater than 0, there exists an n epsilon, some index, after which the distance between any 2 points in the sequence is smaller than epsilon whenever m and n are greater than n. So it's basically the same definition as the definition of the limit of a sequence, except here we do not have an actual limit value. What this is saying, in a nutshell, is that if the points keep on getting closer and closer together, and that after a given threshold they are all within epsilon of one another, then the sequence is Cauchy. Example, look at this sequence here, a harmonic sequence. 1 over 2, 1 over 3, so forth. Intuitively, what are we working with? So we start with the first point here. This is 0, this is 1 over 2 here, 1 over 3, somewhere here, number 4 here, and so forth. After a certain point, all of the points in the sequence will be, well, close to 0, that's true, but also in order for all of them to be close to 0, they have to sort of be close to one another. That's what the definition says. Let epsilon be greater than 0. I am going to pick, by the Archimedean property, an integer n epsilon, which is going to be greater than 2 over epsilon, which I know to be some real number because epsilon is not equal to 0. Then, if m and n are greater than n epsilon, when I look at the difference of xn minus xm, so xn is 1 over n, xm is 1 over m, this is going to be smaller than or equal to 1 over n plus 1 over m, according to the properties of the absolute value. Here, if m is greater than n epsilon, then 1 over m is smaller than 1 over n epsilon, which is twice n epsilon, which, by our assumption about n epsilon, is smaller than epsilon. There we go. We've showed that xn is Cauchy. One thing I will note for you is that this sequence 1 over n does converge to 0. We know that. We've seen that. And it is also a Cauchy sequence. Here's an example of a sequence which is not a Cauchy sequence. So it's the sequence of the partial sums of the harmonic series, which we might also write. Here is how the argument goes. Well, we'll assume, without loss of generality, that m is greater than n. If it isn't, then n is greater than m, and we can do the same argument as we had here, except by replacing, pushing the n's at the ends. In that case, if I look at 1 over n, that is going to be greater than 1 over n plus 1. I put the greater than or equal sign, even though that's technically true, that it is strictly greater than. We're just going to leave it as greater than or equal to to make things nicer looking. I don't have to be super strict about some of these things, as long as what I'm saying is still true. In general, my personal preference is to go with the greater than or equal or smaller than or equal, unless it is crucial to have a strict inequality. So that's going to be greater than 1 over n plus 2 as well, and so forth until you get to 1 over m. Now it's conceivable that m would be exactly equal to n plus 1, which point the chain would stop after only 2 terms. But however many terms there are between m and n, this series of inequalities will hold. We also have the difference between the mth term of the series and the nth term of the series is going to be, given that this is the series that we have here, 1 over n plus 1, 1 over n plus 2, all the way to 1 over n. Do you see why that would be the case? Let me just write it down separately. Xn is 1 plus 1 over 2 plus all the way up to 1 over n. Xm is 1 plus 1 over 2 plus 1 over n plus 1 over n plus 1 all the way up to 1 over m. Because we've assumed here that m was strictly greater than n. So the difference between the two is just a little part here. Okay, so that's the difference between the two of them. And what we've shown is that every single one of these things is greater than 1 over m. So each of the components here is greater than 1 over m. There are in total m minus n terms. So this is equal to m minus n times 1 over m. And I can write this if you want as 1 minus n divided by n. Well, so what we have is that no matter what m and n we pick, and here we've made no mention of m and n being greater than some integer n epsilon. It's just true for any m and n integers, assuming of course that m is strictly greater than n. The difference between these two terms is always going to be greater than 1 minus n divided by n. So it's true, in particular if you pick m as twice n. So once you've picked an n, your corresponding m will be 2 times n. So once you've picked a term in the sequence, the term xn, we're also going to look at the term which is twice as far in the sequence, term 2n. The difference between these two terms is always going to be greater than or equal to 1 minus n divided by 2n is equal to 1 minus 1 half, 1 half. So no matter what epsilon you pick, there cannot be an integer n after which xm minus xn will always be smaller than epsilon for every m and n, because if you pick an epsilon which was smaller than 1 half, you would find that the difference between at least 2 of the terms in the sequence is always greater than 1 half. And that's not going to give you what you want. So this is not a Cauchy sequence. Sorry, here I wrote for every epsilon greater than 0. What I meant to write is for every n and n. I'll remark as well that the sequence of the partial sums of the harmonic series cannot converge, because if you do remember from calculus, we've seen that the harmonic series does not converge. So we've seen one example of a Cauchy sequence, which also happens to be a convergent sequence, and another example of a sequence which is not Cauchy and which happens not to converge. In fact, over the real numbers, being a convergent sequence and being a Cauchy sequence are equivalent notions. That is not going to be true of every space. Over Q, the set of rational numbers, being a convergent sequence and being a Cauchy sequence, not the same thing. In fact, we create R, the set of real numbers, by completing Q, so that every Cauchy sequence in Q would also be a convergent sequence, except it can't converge in Q, it has to converge in some other space. There are holes in the set of rational numbers. Now, the holes that exist are the holes, points where sequence would converge if that point was in Q, but it's not in Q, so it doesn't converge in Q. These are Cauchy sequences in Q. And so we fill R, we complete R by filling the holes, by basically making it so that every Cauchy sequence in originally Q, but also this new space R that we've created, will also be convergent in R. Every Cauchy sequence in R is convergent, every non-Cauchy sequence in R is divergent. Before we get to that result, we will show the following. If Xn is a Cauchy sequence in R, then it is bounded. No, we just need to find the bound. So what are we going to work with? We know that the sequence is Cauchy. So if I give you an epsilon greater than 0, particular, perhaps an epsilon which is smaller than 1, let's restrict ourselves to a specific interval of epsilon values. It's going to be true for every epsilon value, but that's the case. It also works for epsilon values between 0 and 1. Whenever we pick one of these epsilons, we have a corresponding integer n epsilon such that the distance between the term xn and the term xm is smaller than epsilon when n and m are greater than n epsilon. Well, we're going to pick a specific m, call it n epsilon plus 1. So whatever n epsilon we got from the definition of Cauchy sequences, let's add 1 to it. And that's going to be something we call m star. And if it is the case that n is greater than the same n epsilon that we found before, the absolute value of xn is going to be equal to the absolute value of xm star plus xn minus xm star. Just added 0, but I've added 0 in a specific way here. By the triangle inequality, this will be smaller than the absolute value of xm star plus the absolute value of xn minus xm star. Now we know that this term here is smaller than epsilon because the m star that we've picked is greater than n epsilon, and when the m star is greater than n epsilon, the difference between xn and xm will be smaller than epsilon whenever n is greater than epsilon. That's part of the Cauchiness of the sequence, if you want. Now we will pick a bound m, which will be the maximum of the following value: x1 plus 1, x2 plus 1, all the way up to xm star plus 1, using, of course, the absolute value. In that case, xn, which we know to be smaller than xm star plus epsilon for every n, will also be smaller than m for every n. We've picked this to be the case. It's going to be smaller than xn plus epsilon, for every n because of this bit here. And then there's all the terms that come before m star. There might be a lot of them, but there's a finite number of them. So we can find an m, a bound, which is greater than all of these up to this point, and then the Cauchiness of the sequence takes care of that last bit here. What we've shown is that every Cauchy sequence is automatically bounded as well. The property of having all of your values getting closer and closer and clustering on top of one another implies boundedness of the sequence. You can't suddenly at some point take off, even if you come back after. You might take off, and then when you come back, you say, well, it's bounded by wherever that one point has taken off to, but you can't indefinitely take off. You can't, every 200 observations get a larger and larger value, even if you come back here. You would not have a Cauchy sequence. This isn't the way Cauchy sequences work. They are well behaved with respect to boundedness.